And welcome back to another episode of the Game Engine series. So today's a pretty exciting episode. I think this is going to be the most complex thing we do. And at a surface level, it doesn't sound that complex and there isn't any it's crazy code. But what we're going to do is look at buffer layouts. So what does that mean? Well, when we upload our data to the GPU, we specify the way the data is laid out in our vertex buffer or index buffer. Right? What I've done is I created a package called Zimp, which I'm still working on it, but it's basically going to be our asset pipeline. It's what's going to turn object files, GLTF files into meshes, but in such a way that we turn this interwoven data and put it in a straight and easy to use or easy to consume for our game engine. So we're turning the generic .obj files into a highly optimized format for our game engine. And that's what the tool is going to use. So we're going to add that tool in, and during build time, it'll automatically convert those file types. Then all we have to do is now read that, which reading from that file is given from the library. I added that. So we'll read that and we'll have our, let's say, Z mesh, if we're looking at meshes. And then once we have that, we can use the format in there to specify our vertex buffer. So what's optimized for game engines is not highly interwoven data. Like I said, it's what's known as SOA or structural arrays, where each kind of data, so let's say positions of a mesh, normals of a mesh, tangents of a mesh, they're given in their own contiguous blocks or contiguous arrays. So when we upload it to the GPU and shaders are reading it, they can just very quickly go through all the positions, go through all the normals, and do what they need with those instead of trying to jump. If you just need the normals, it's jumping however many spots to look at normals if it's all interwoven. So again, what we do today is we create our layout system. So it's quite a bit of changes to our vertex array, some changes to our buffers. I know we kind of just did a little bit of refactoring there, but this is a bigger change. It's going to set us up for the future. We really shouldn't touch it again anytime soon, maybe minor tweaks if needed. But once this is there, it's there and it's a productionized system almost. Because we're optimizing these vertices, like I'm doing that with the Zimp tool I wrote. So we're going to hook into that. And yeah, I hope that's exciting for you. I know there could be some debate about the fact we're not writing every single line of code. We're not doing the optimizations in the videos. If you want a video on Zimp and the whole pipeline and how that all works, please let me know. Leave a comment, like, subscribe, all those things. And to just let me know that that's what you want. In the code part, I do quickly go over what the pipeline looks like in Zimp, but if you want a very detailed breakdown, please let me know, leave a comment, and I will make that video. But yeah, there's also a little bit of code at the start to just refactor our scenes to allow error types to be returned. I should have handled that from the start. So I don't write the code live on camera, but I show you guys all the code. And then I also, at the very end of the video, I'll show you again how to get to the repo and look at all that code. So if you want, there's some timestamps if you want to skip right to the end and make sure you have that code before jumping in with the video, follow that. And yeah, like I said, it could be highly debated that I'm not writing every single line of code on the videos. I want this game engine to actually turn into something that people can use. I want to show people how to create a proper game engine, make something that works well and is truly productionized. Like we could have just quickly parse OBJ files and then have the data interwoven. That's not optimized. We want to make things as good as possible. And I want to give you guys the resources to that. So go look at Zimp, go look at that tool, see what it's doing. And if you want to go write that yourself, or if you can see an improvement, go write it yourself or add a PR or anything like that. Highly encourage you guys to do that. And yeah, I just want to keep the series moving. I want us to get to some cool stuff. I want to be able to truly make a game engine that, like, if anyone's following along every episode, they're in a spot where they have a true game engine. They can make a game and it works well. It's not laggy. It's not slow. It's a true game engine. And that's what I want for the series. And sometimes that's hard, writing every single line of code, especially when it's refactoring and things like that. So let me know what you guys think, because if you want to keep the series moving faster, making lots of progress, we can't write every line of code on video. But if you guys wanted to slow down, break down every line, please let me know and we'll see what we can do. But yeah, this is a big episode. Not going to take too much more time, so let's just jump into the code. As I said before, we have a lot to get through this episode, but I just want to quickly share where you can find this. So if you look for Zimp, this is what we're going to be using today. This is what I've been working on. It's still very much in development. The only thing we actually have so far is GLTF parsing, but we're going to use that today. And basically a quick overview of how it works is we're going to add a GLB file. We're going to add a step that automatically discovers and cooks it, and it's going to turn into a Z mesh. And once we have our Z mesh, we will be able to just very easily render that with vertex arrays. So we're going to do a lot of work around the buffers, setting it up, because this gives a full mesh that we're going to use for the rest of the game engine. This is going to be in production once we get there. So this is very important. So one thing I want to quickly go over first is I will show the commit. One thing we need to do before this episode is make sure that all our scene types are able to take an error. So before it looked like this, it was just void. But now by adding the exclamation point, it can be errors. There's quite a bit of code that need to be updated. So just to quickly look at a diff in here, see there's not too much actually in the editor, just simple catch, but there's quite a bit of code in here. So just to quickly look at it, we can see in its scene, we're catching the errors. So we're kind of just propagating up the errors. There's just a lot of places where we add a try. So yeah, there's a lot of places we're just adding like any error type, adding try, and a lot of places like that. And same with the vtable here, we can see now it's any error or void. So just a lot of that. What I'm going to quickly do is do episode 13 pre-code. So if people want to go look at that, that'll be on the repo. I'll do the same thing with this. Episode 13 pre-code. So that will be in the repos, in the YT branch as always. So if you want to get to where I am at, go look at that code. And now let's get into it. So as always, I zoomed out just so I could show everything, but now let's zoom in. So one of the first things we're actually going to do is install Zimp. And now inside of make sure you're in runtime, we'll run this command. It's going to fetch it and it resolves. But now if we go over to our build.zig.zon, we can see there is an official release. So I'm sure if you run this again, this will get updated, but let's add it to our actual build.zig. So there's going to be a couple things. One, we're going to import it actually right here. And just for the simple fact that we're going to re-export to our editor or sandbox app, the actual build step that we're going to add. So again, this may not make sense if you're not as familiar with Zig, because this is not something you'd really see in C++. But hopefully this will make sense a little bit later once we actually add it. I'm just getting us ready. But besides that, let's just do our normal. We'll still need it as a normal dependency. So let's call it Zimp and dot target equals target and dot optimize equals optimize. Now that we have that, just go down. So let's call this Zimp, Zimpdep, and Zimp. Let's copy that and just really add it everywhere. So lib unit test root module. And now we should have it everywhere. Again, it might take ZLS a while to actually index and get imports, but we will keep moving on. So just to quickly, once again, explain what Zimp actually is it's going to be a step we add in our build system. So we will have all our assets in a file or a folder, and the build step will automatically scan for all these file types and then turn it into like a game engine optimized binary file, which then we will just read like the Z mesh files in our actual game engine. So we never have to worry about trying to parse like all these three can all be for meshes. But what this whole pipeline will do is turn all those into Z meshes that we can just consume very easily. It's a very cool thing, and I've been spending a lot of time on it recently. So I hope it makes sense to people. But in order to actually do that, we are going to need quite a bit of code, and it's going to start in our graphics. So we're going to actually be making a big refactor to Vertex Array and a smaller refactor to buffers. I know buffers have been used a lot, but hopefully after this, it'll be pretty simple. So what do we need for meshes and rendering meshes? Well, we need layouts. We need a way to actually know what the layout is, what are the data types, how do we structure the buffers, things like that. So let's start with that. So we'll have a stream attribute, which streams are going to be almost like buffers. So I know we call this vertex. Let's see, this one vertex buffer. If we're going to generalize it to more just be a OpenGL buffer, which stores obviously vertex data, but all our data that we're going to use. And again, hopefully I'm going to try and just explain it as we go. Like I said, there's a lot of code to write. So I want to keep moving on the code and explaining as we write it. Normalize bool. So these are all just kind of things that we'll need for what the stream is. So I'm actually just going to copy, paste a few things in here. Anything that's very repetitive, I probably will say just for the sake of episode length. So these are all going to be all the types we support. So floats, matrices, ints, shorts, all those. So then again, I'm just going to grab the rest of this and explain it as it's written. So we have size. So a float is obviously 4 bytes. Two floats is 8 bytes, etc. When we look at the component count, that's actually how many elements are in it. So a float is just 1, but a float 2, we're saying it's 2 floats or 2D vector. So there's 2 elements. Or a math 3, that's a 3 by 3. So there's 9. So hopefully that makes sense. And then we will just need to know which ones are integers. So these are them and not. Okay, so now let's head over to buffer and make the changes we need in here. So let's first get standard library because we will need that. We will also need index format. So this is coming from Zimp, and I really highly encourage people to go take a look at Zimp. It's, again, I've been spending a lot of time on it, and only GLTF is supported right now. Gonna be adding more as it goes on. It's been a lot of fun to work on. Okay, one of the first things we need to do with our vertex buffer is actually turn it into a more generic, just a byte stream. So U8's like, it's just individual bytes. So now when we actually bind our buffer data, and let's actually make this a little bit easier to read. Let's see. So size is actually going to be data.len, and then this would be data.pointer. So it's all the same, but now just a little bit more generic. And then let's also provide a function to almost provide backwards compatibility and just make it actually like a little bit easier to work with if you know your data types. So data const t, then we can just return, and this one will be buffer error or vertex buffer, return init std, this is where we need std for, as bytes data. So hopefully that makes sense. Let me actually just move this up here. So we could almost like use it right now if we wanted to switch, because before we would do vertex buffer.init and then we would pass vertices, right? Like that's what we were doing before. But vertices is a slice of F32s. So if we wanted to use this new method, be from slice F32, and then we'd be able to pass it. So I hope that makes sense. And then one thing I never added was a dinit for these, which I think will just be helpful. GL delete buffers, because we weren't actually properly deleting the buffers. So yeah, self.id equals 0. We can actually add this exact same function down at the end of index buffer. And now we are going to make a small change over a little bit, actually, I guess a little bit more of a change to index buffer, because now we have that index format coming from Zimp. Format. And now we're going to kind of change the name. So again, we have to do, instead of from U32s, it's going to be U8. We'll need a count, and then the index format. And then count equals count and dot index format equals index format. So again, we're gonna have to do something similar here where we can just do data.len instead. And let's rename this to data because it's raw data and data. So all that's going to stay the same. This is can remove one line here and might as well make it const pointers because we're holding more things and dinit. So we're going to have to add one thing up here. So this one actually shouldn't be public because that's not how we're going to initialize anymore. So if we look, we have index format, which is just U16 or U32. So if we have a small enough index count, we can save memory and just make things a little bit leaner by using an array of U16s, U16. But if we know we have lots of indices, then they will need to be U32s. So init U32 indices const U32 buffer error index buffer return init raw std and slice as bytes indices, and then we'll need indices.len. So the reason why we have to start passing indices.len is because we can't just use data.len, because now, say it was U32, the actual count is different. So turning U32s into U8s 4 bytes would be 1 U32. So it'd kind of multiply by 4. So hopefully that makes sense. Instead of being U32s, it'll be U16. And all of these will be U16s. So that's all we should need for buffers. Now this is probably going to be the biggest change out of anything. So let's go over to our vertex arrays, because remember, in OpenGL, vertex array is kind of just the backing data mechanism that OpenGL gives us for a mesh. We can upload all the data and then they'll be there for our shaders. So let's head back to the top. So things are going to switch. Instead of having a single vertex buffer, we're now going to have a bunch of streams, which the streams will make sense once we get into the Z meshes. So max streams will be 8. And we'll have streams, max streams, and then it's an optional stream. And then the actual count, because it may not fill it, we'll have to keep track. So if we remember, we just wrote stream. That would come from, where was it? Layout, stream attribute. So I guess we haven't actually written stream yet, but we will need stream attribute. So then let's write what stream is. It's just an internal struct, which will have the backing buffer, so vertex buffer, or stream attribute, which will be a stream attribute. So now we know what streams are. Init will change a little bit. So now we're not going to pass vertices and indices. We're actually going to pass nothing. And it simplifies this quite a bit, because now we don't need really any of this, because it's going to be created a different way. So streams, remember they're optionally null. Max streams and stream count default to 0. And you will be undefined for now. So now we're going to add a function called pub function add stream, which will be the vertex array itself, the data for that stream. So again, a stream is just a vertex array or vertex buffer, not vertex array. It's a vertex buffer in our code. So things do need to be laid out a certain way. Error or void. GL find vertex array self.id. So remember, we have created it. So we bound it. So now let's actually create the vertex buffer. Once VBO equals buffer dot vertex buffer. So now we're passing that data, and then return vertex array error dot vertex buffer creation failed. And now we can actually bind that buffer, and we will need the location. So again, when I say location, if you remember here, it's going to be the same location from that's in our vertex. So we look at Z meshes. Let's just go look at them. So do I have Zimp anywhere? I think I have Zimp here. Okay. So if we were to go look at a Z mesh, it's going to have this. It's going to have our positions, which are our positions. So it's these. Then it's going to have optionally, so we always have positions, then it can be normals, tangents, UVs are texture coordinates, or joint indices. Then it'll also have our index buffer, or the actual indices. So when I say a stream, what I'm saying is a layout location. So that's what I mean when I say that. Hopefully that helps clarify things a little bit more. Now let's get back to it. And then our data type is attribute.data type. So now let's enable vertex attrib array, which is something we have done. And now we need a quick conditional check. So we remember we just wrote that. Then we'll do GL vertex attrib pointer, but it'll actually be I pointer for int. So now if we look at it, location, and this OpenGL code, so it's kind of like giving it the structure. Type, int cast, size, and these are all contiguous blocks. So the stride, we're not really interleaving data at all. And that's the benefit of this. It's a struct of arrays, essentially. So if you've heard of that in maybe something like ECS, we're optimizing data. So every layout, every location, it's its own buffer, and it just has the straight array of data. There's no interleaving. There's no having to look things up. And it's a lot simpler. So let's take this, get rid of that I. Then quite a bit of similar things, but this one, if attribute dot normalized, GL true, else GL false, and cast size. So now after we've done that, we can do self.streams, self.stream count. Now we can actually create that stream. So the VBO equals VBO, so the vertex buffer, attribute equals attribute, self.stream count plus equals 1, and then unbind. GL bind vertex array to 0. Next thing we'll have to do is add a function for set index buffer, because it will happen at a different time now. Vertex array bo buffer.index buffer, GL bind vertex array, self.id, vbo.bind, GL, and then you unbind vertex array, self.evo equals cbo. And then this one I actually forgot to do last episode, I think. We no longer need set layout. And now draw does change a little bit. So first we need the GL index type. Oops. Switch self EVO index format dot U16 GL unsigned short. And if it's U32, GL unsigned int. So now, if I go here, so now we have triangles. Instead of hard coding a count, as I said we would fix, self.ebo.count. And then we'll have GL index type and null. And then one thing like we added for the other ones is going to be a dnet function. So for each stream, so if we have stream, lots of pointer manipulation here, s.vbo.dnet. And then we can also set it to null. And then self.index buffer dnet, GL delete vertex arrays. We're just deleting one of them. Self.id equals 0. We are going to have to do one more pretty big one that I am going to paste in and explain. So we're going to call it mesh.zig. Okay, let's start with the easy stuff. So first, dnet and draw is just directly calling the val because we hold that. AB are bounding boxes. We won't be using those today, but we'll be adding them in the future. So now what we're going to do is we're going to turn that Z mesh, which I was talking about, which we will just load from a file. and then turn it into a mesh handle. So this is now what people like game engine developer, or not game engine, but game developers will use these handles to actually more interact with things. So then once we do that, we look here. One, we know our first location. So again, location is this. So location is 0. This will always be the case. We're always going to have every shader with position because it's guaranteed with a mesh. And then starting at location 1, we see it does the mesh have normals. So now we're creating a new vertex buffer and adding all those normals. So if it had normals, we do something like this. Location 1, we'll just call it normal. So then if it had UVs, then we do something like this. 2, which I don't think this one's a vec 2, but AUV 0. So then it'd be things like that. And then for all the different types, then this depends on the type, but we can either create the U16s. Remember, we wrote these functions init U16 or init U32, depending on what indices are in the mesh. So that's kind of it for the mesh. Now let's get to, I'd say, a lot more fun stuff. So now we're going to actually hook up the Zimp build pipeline. So let's head over to root. One thing we will need is, what gets the game is Zimp. Once cmesh equals Zimp dot cmesh. So a couple things I know we're gonna need actually, so let's just get it out of the way, is IO. Now that we're in Zig 0.16, we will need IO. It's gonna be passed here, sc.io, and then just .io equals IO. We go inside of init scene, do self.io, or app.io in this case. Init scene will now take IO. Again, this law of propagation, because now on startup is going to take sc.io. IO sc.io. I'm going to have to add this in a few places. So on startup, IO sc.io. IO. Down here would be IO. Then look on startup. So this one doesn't have it. Search on startup. So that one has it. 2, 3. That doesn't need it. That has it. We'll have to pass it here. So now I think that's about everything we need in runtime. Let's go over and actually start to do things. So again, let's just follow up with that IO change. So this is actually a pretty nice thing. Oops. That comes from Zig 16. Is now we can do init.bpa and then init.io. So we will eventually specify our own and be more optimized, but now let's do the fun thing. Let's go over to build and import Zephyr runtime. Okay, you know what? Let's just try and get a build back. See, we have nice error messages. And underscore equals IO. So after we have our runtime mod, we're going to add the Zimp dependency, which will come from runtime dep.builder.dependency. So we're basically going into our runtime and finding Zimp. And target equals target. And optimize, this time you're actually going to do release fast, because you want the Zimp builder to be as fast as possible. So it'll take a while to build the first time, but then after that, it'll be very fast. And unless you're updating Zimp often, which maybe at the start we are, but in the future we won't, we want that to be fast. We're adding this cook step, which is coming right from the Zimp package. And what it's going to do is, one, we provide two options, one source dir, and then an output dir. So let's make that. So we already have our assets folder. So you might not have meshes, but let's add that. And then what we're going to do is right beside it, we're going to create an output. So what this will look like is source/assets. This one will click source/output. Now we'll have a cook step, b.step, call it cook assets with Zimp, and then cooks up. Let's get rid of that. Dot depend on cook.step. So if you manually want to cook up your assets, that's what this does. But we're also going to make it automatic by doing, let's see, under depend on run, or one sec, where am I looking? It'll be this one right here. Run command dot step dot depend on cook dot step. So before we actually build the game, it's going to cook our assets. So if we go back here, we might be able to see it, but maybe not. Okay, so we see that did fail to build, but we see our build step's still going right now, and that's because we're building Zimp. See it right there, we're building the exe of Zimp. Okay, and there we can see, so obviously we have our compile error that's expected, but we also see in here from Zimp, right now it scanned, it found 0 assets, but then obviously cooked everything. So now let's add an asset. Okay, so I have this one asset that I'm going to copy. It's just going to be a simple triangle mesh, and I'm going to put it inside our meshes. So now we have that. We should be able to see it in here. Look inside of meshes, we see we have that triangle. So it's not going to, it's a GLTF file, but it's just a simple triangle mesh. Okay. So now if we go ahead and run again, we look, it happened right at the start now, but it found that triangle file, found that it's a mesh, and then it cooked it into its own file. So it cooked that file. And now if we go over and look at output, we see we have the Z mesh. This is what I'm talking about. This is what Zimp did, turned the triangle into a Z mesh. Okay. And that's pretty awesome. So now let's actually start to use it. So right now we have everything hard coded. We don't want that anymore. We'll just get rid of it. And we'll also grab onto mesh handle, which I don't think we exported actually. So let's put that here. Pub const mesh handle graphics. Let's see, that's going to be mesh.mesh handle. So now we have that. So LSP restart. We have that again. So now instead of holding a vertex array, we're actually going to hold a mesh handle and call it a mesh handle. Nice. So now we're not going to have vertex arrays anymore. Just get rid of all that. But now after we do the allocator, we're going to now need our IO. So what we're going to have to do is eventually we're going to make our game engine handle opening these files. But for now, we're just going to do it right here. So we're going to open this zmesh file. So first we need our current working directory. And then we get the mesh file dot open file. And we know it's source output. You can look at the name, but triangle dot zmesh and var mesh equals try zmesh dot read allocator IO and that mesh file. So I don't think we imported zmesh. Let's get that down here. cp.zmesh. It's not coming back down. We have that. So again, zmesh is from Zimp, and we provide a read function which will read as .zmesh file into a zmesh struct, and now we can work with it. So let's just first defer dnet the allocator, and now self.mesh handle equals mesh handle dot load from mesh. Do the mesh, and then we just try. And also, because of the error handling we did that I showed at the very start, you don't have to do that because it will be caught by our application. I didn't mean to try there, but try goes right here. So now that's pretty good. But if we come down here, it'll instead be mesh handle. And we'll also have to do dnet. Okay. And there's one last thing. So this GLB or GLTF file does include normals. So we are going to have to update our shaders to be able to handle that. So remember, like I said, how if there's more than one layout or stream, we're going to add it here. So that's exactly what we're doing. And the way it is they're octal encoded. So we're going to have to decode that. So I am just going to paste that in. It's not a lot of code, but the episode's getting long, so I want to keep things going. So instead, we'll do our decode. Instead of vertex position, that doesn't change, but B normal is now decode oct normal A normal. And now because we're kind of just triangulating colors, now we're going to visualize normals as a color map between -1 and 1. So color equals V normal. So instead of in of vertex pause, it's going to be V normal, which if we go back, that's the out is V normal. So V normal prime 0.5 plus 0.5. And now it's just going to be color 1.0. Okay, there's a lot of code that we just wrote. Cannot guarantee it'll work on the first try, but let's attempt to. So as we see, it cooked the mesh. So you can see, okay, file not found, incorrect alignment, but error initializing scene. That is because this is spelled wrong. So we go triangle. We now delete this. We run it. There we go. Wow. Okay, so it worked first try. So now the normals aren't really doing anything in this case, but it is a simple color, and we're moving around the triangle, which is exactly the mesh. So you can see, you can also turn off debug if you want, but you can see we cooked assets, we started, cleaned up the game scene. It's very cool. So yeah, that is the episode. So now this is going to make it so much easier for us to add on meshes and other stuff in the future. It's going to be very easy to add like any 3D meshes, anything like that. And then we're also going to use Zimp for every sort of asset for optimizing textures, animations, skeletons, everything like that. Zimp's going to be used. I'm still obviously working on it, but yeah. And again, let me just do this. Episode 13. And episode 13. So as always, if you want to check out the code, so you'll come to, let's say, runtime or editor. You go to the branch, go over to YT, and then you just look at the commits. And now we can see like that pre-code from the start. You can find it all here. Again, not too much. Or if you wanted to go find the asset file we used, we can go here. So we're on YT branch. There's assets, meshes, that triangle.glb file. It's going to be right there. So yeah, big episode, lots of code, but hope you guys enjoyed it. Okay, and that was the episode. I hope you guys enjoyed it. I had a lot of fun making it. Working on Zimp, I've actually had a lot of fun the last couple of weeks, more than the game engine itself. I just think it's a really cool tool, and it gets you thinking about, there's all these different kinds of formats, but they're general. How can we optimize it for our game engine? And I have a lot more things to do with Zimp. I'm gonna be working on it for a while, but just having a lot of fun. And it's nice with the game engine because there's so many different things to build. I can go branch off and work on this for a while and then come back to the game engine. Keeps me excited, keeps me motivated to keep going. And yeah, please let me know what you guys thought of the video. Again, it might be controversial, not writing every single line of code, not writing all of Zimp on YouTube. That really something that big, it's not really possible. So yeah, please let me know down in the comments. And if you enjoyed, please like, subscribe, all those things really help. And as always, Discord's down in the description. People chatting in there, it's always fun. Let me know what your thoughts are. Yeah, have a great day.